So we were talking about variational calculus, and I spent an inordinate amount of time working through the Verkristochrone, which was fun. But if you look in the two, I was going to say you really should be looking at the 2017 notes, because I've added a little bit there's a little bit more there, mostly just a picture, and I think I finished working out like the minimal surface area being the I think it's the surface of revolution formed by like Koch. Like that's worked out there, minimized. Like you find the minimal surface area. You can look at that as a variational calculus problem. So that's in the notes. You can look at it. Now I still haven't had a chance to think properly about this business here. I still feel like there's something wrong in it, but I have to like let it go at the moment. I have to let it go. So I mostly just want to talk to you about physics a little bit, and about like Lagrangians versus Hamiltonians, just a little bit, just a word or two, and maybe just show you an example. And if we had a working projector, I might do more, but it is what it is in here, right? But yeah, the Lagrangian we can look at as kinetic energy. Just a second. The coffee machine, I think the coffee machine is making a noise.
Oh no.
But I don't think it's on.
Really a noise?
I don't know. Am I wrong? I don't know. Something seems askew in there. Okay, so sorry, distracted by the smell of burnt coffee. This is the Lagrangian in 2 dimensions, right? If we're in 3 dimensions, of course, so this is 2D, right? In 3D, you could write, kinetic energy is still 1/2 mv squared, but then it's 1/2 m. And in physics, we usually use spherical radius, so like it ends up being. We use in physics we use r for like the rho. Fine, let me. This is the time I can't make up my mind. Plus, how's it go? R squared. Oh goodness, I can't remember. Oh man. Rats. Well, what you do is you just write down x equals to, so here's the physics ones. So they do their theta and the phi kind of opposite of we usually do. And so when you calculate x dot squared plus, first of all, of course, you can write the speed squared as x dot squared plus y dot squared plus z dot squared. And then if we actually work that out and just, differentiate it, related rates kind of calculation, chain rule if you like, when you do x dot, y dot, z dot, for instance, you've got, x dot is, r dot cos phi sine theta minus r sine theta, sine phi rather, sine theta, phi dot, plus r cos phi, cos theta, theta dot, and so forth, right? My bad. All right, so there, there it is. Oh, and then you square those and add them together, and cool stuff happens, right? Like you end up getting r dot squared plus, r squared theta dot squared, and then plus, as it happens, r squared sine squared. I think it's sine squared theta. Let me think about this for a second. In this setup, this is our theta's off here, phi's down here actually. So this right here is actually our sine theta. So essentially that's playing the role that r did in 2 dimensions. And so that's why you get an r squared sine squared theta phi dot squared here, if I remember right.
Can you remind me why they used the dot?
Oh, just time derivative. The dot's just time derivative is all. It's just so it's easier to, it's just a nicer notation. It's Newton's notation for derivative, actually. Okay, so that's there's kinetic energy, what it looks like in like Cartesian coordinates versus spherical coordinates in 3 dimensions. And so, we could do things like, I don't know, for example, if I could set it up right. Suppose you've got you've got like a ball here, and it's on a string of length L, right? And it's free to kind of pivot one way around. So this is sometimes called a spherical pendulum. The question is, what would the equations of motion be for a spherical pendulum? Well, I think essentially we could just, there's various ways you could do it, but I guess if we use spherical coordinates, we could do that maybe. I guess I don't usually, what's usually done in physics is you just kind of like write equations for things and differentiate them, as opposed to using like formulas you already have, like more often than not. So the question is here, well, what's potential energy? So like potential energy, right, is mgz essentially. If we're near the surface of the Earth, that's the potential energy due to gravity. And so if we put z equal to 0, like up here, if I drop an angle off the vertical, right, then I can, oh, I'm sorry, Ernesto, my mind's not working well enough to do this example, I'm not sure. I need to come up with an angle. Let me call that alpha, all right? because it's not quite the same as the theta over there, see? But anyway, what's my z? Well, I believe what I'd have is something like minus mg L cosine alpha, given that setup. That's like how it's down, that would be its z. And now, of course, then I can also talk about it, rotating around, and I can kind of like, measure its current angle beta like that. Now that won't give me any kind of, right. Right, that's not going to play into the potential energy at all, but it does need to account for, because it will matter for the kinetic energy. So, all right, so what I usually do in this kind of situation is regret my choices. No, I do something like try to sort out if that's how I probably chose poorly my coordinate setup here. Like usually what helps me then is if I can write x equals to something and y equals to something and z equals to something for the coordinates of m, then I can figure it out from there if I'm stuck. So if I put the origin up here, which is kind of annoying, but I seem to have done that, if that is my choice, and let's just say it's my choice, right? Then x, and we can look at that circle as if it's up here, right? And we can measure let me measure the beta like this way, right? So yeah, like the usual. All right, so beta. So x would be equal to like,
Alpha sine, that's already.
Oh right, this distance is what? Yeah, good point. That's L sine theta. So L sine.
Sorry, L sine.
Yeah, L sine alpha. Thank you. I'm kind of brain dead today. Sine alpha times cosine beta, I suppose, if I had these things set up right. And this would be like L sine alpha, sine beta. And z is, well, it's just minus L cosine alpha, right? And then L is given to be constant. So so then I do like x dot squared plus y dot squared plus z dot squared, right? And how does that go? Well, it's going to give me like a, let's see here, L cos alpha, cos beta, alpha dot, minus L sine alpha, sine beta, beta dot squared plus L cos alpha, sine beta, alpha dot plus L sine alpha, cosine beta, beta dot, square that,
And alpha dot is 0, correct?
minus, no, alpha dot's not 0.
Alpha doesn't change.
Alpha and beta are both functions of time.
But
They-
does alpha change?
Alpha can change, yeah.
I'm staying in that.
Oh, no. This is a spherical pendulum. Alpha and beta can both change. That's what makes this something we wouldn't talk about in Physics 231.
Right.
Yeah. Unless I was really misbehaving. But probably I wouldn't misbehave this much. Anyway, so, and then this last one's just L sine alpha, alpha dot. You gotta square that thing, right? So this is the formula for speed in terms of these coordinates that I've just invented, alpha and beta. And this is kind of signature of classical mechanics. This is practiced by physicists They invent coordinates that suit them and work out the math. Or just claim the math and don't really work it out, but they know what they're doing, so they usually get it right. They check edge cases, stuff like that, you know. So when you square this out, you notice you've got cos cos, sine sine, and over here you've got cosine, sine cos. So I think if you look at it, you've got a cosine alpha, sine alpha, cosine beta, sine beta, cosine alpha, sine beta, cosine beta. You've got the same 4 sine cosines in alpha dot beta dot. One gives you a plus, one gives you a minus. These are going to cancel, the cross terms cancel. And it just leaves you with like this squared and this squared. But when you look at this squared and that squared, you get a cosine squared beta plus sine squared beta, which just drops us back to L squared cosine squared alpha, alpha dot squared, right? And then of course you've got your plus, then the square of this and that. Now square of this and that, we've got again a sine squared plus a cosine squared in the beta. So we just get an L squared sine squared alpha. Looks like a beta dot squared, yeah? I did that right. And then of course you got the other term over there, plus the L squared sine squared alpha, alpha dot squared. Now 2 of these things should go together. And so that gives us L squared alpha dot squared plus L squared sine squared alpha beta dot squared. In fact, the truth be told, most practicing physicists or students of physics in the midst of these kind of courses would just write that down. Because you can see that if you look at a little ds, if you look at a little arc length subtended holding your other coordinates fixed while varying alpha, if you just vary alpha a little bit, right, like this, that ds, well that's going to be what? It's going to be equal to L times, you know, d alpha dt dt. So like, you know, ds dt along that, just changing alpha and fixing beta, you're going to have ds dt is just L alpha dot, which is that. On the other hand, if you imagine instead of going along, and I know it's hard to see my picture, but suppose you're over here, right, and you're just going like that. Well, that ds depends on, as you pointed out, that radius, right? And the radius there is L sine alpha, right? So I do L sine alpha times like d beta dt, because this little, you know, that's a little d beta. If you can, my picture's too stupid, but that's why we have this L sine alpha beta dot squared terms. That's the part of the speed. So you can do these kind of fix your coordinates, let the one vary, look at the infinitesimal arc length subtended with respect to that coordinate and figure out the contribution to the speed from there. And anyway, so there it is. And now what do we have? Well, we've got the Lagrangian. Our Lagrangian is simply L is equal to, you know, 1/2 m. Well, it looks like we could factor that L squared out, right? 1/2 ml squared. And then we got ourselves an alpha dot squared plus sine squared alpha beta dot squared. That's my kinetic energy. And then I remember Lagrangian is T minus U. So that minus and this minus give me a plus mgl cosine alpha. And so that's my Lagrangian for the spherical pendulum as I have it set up. And then we can write down the Euler-Lagrange equations for the motion. Like, for instance, let's see here, for alpha, I have partial L, partial alpha is equal to d dt of partial L, partial alpha dot. Let's see here, so partial L, partial alpha is literally m L squared sine alpha, cosine alpha, right? Because when I differentiate the sine squared, I get 2 sine cosine. And that 2 cancels with the 2 to give me an ml squared, like that. And then beta dot squared, right? That's my partial L partial alpha. Oh, there's lots of alpha dependence here, isn't there? And then this one too, right? Minus mgl sine alpha is equal to what? ddt of partial alpha dot, which is what? Well, partial alpha dot is just that term. So I get a an m l squared alpha dot. And the 2 cancels like that, right? Alpha dot, rather. And so there's one of the equations which defines the motion of the spherical pendulum. Of course, you could rewrite that as an alpha double dot over here and pull out the ml. And in fact, there's an ml you could cancel across this whole thing, right? Now the beta equation, on the other hand, is a little bit easier. I should have done that one first. The beta equation, well, partial L partial beta is 0. So we have partial L partial beta equal to ddt partial L partial beta dot, which in this case tells me 0 is equal to, all right, so then what? ddt of partial L, what is partial L partial beta? So the only beta dot dependence is right here. So it gives me a 2 beta dot. That cancels this 2. And we've got ourselves an m l squared sine squared alpha, right?
What do you mean by partial L, partial beta if L is not dependent?
Well, that's it. Partial L partial beta is 0.
Oh, I thought you meant little L. I'm sorry.
Oh, no, no.
I see.
And let's see here. So that right there is a constant of the motion. Essentially what that is the angular, it's the angular momentum in this sense. The angular momentum in the other sense, it's coupled to gravity, as you can see through this equation, like the angular momentum about the, the vertical angle, it's coupling into gravity, swinging back and forth, whereas this one is just whatever it is. If you start it going like that, it will continue going at that rate. According to this relation right there. But there you go. That's the spherical pendulum. Now, let me show you another one here. I'll have the good sense to not try to do the geodesics on the sphere this year. Every time I try to do it, I get stuck and I regret it. So I'm just not going to do it. You say, well, you should fix it. I should figure out how to do the geodesics on the sphere so I can lecture on it competently. Yes, I should. I absolutely should. And as soon as I have time to do that, I'll do it. But I don't yet. So maybe in my retirement, I don't know. Hey, once they start paying me for this course, how about that? You know what I mean? But no, I do love this course. Another example I usually give is just like a double pendulum, which is a little bit easier. So you got M1 and then M2 down here, like this. And so you can say, well, this angle is theta 1, and the angle that is off the vertical here is theta 2, right? And this is maybe L1, and this is L2. Then in this situation, the kinetic energy I can just write down. Okay, what is it? It's you know, it's L1. Oh, this is where I'm going to get into trouble if I just try to do it. I'm going to miss a term. Dummy. Okay, so, all right, so if, goodness gracious, if this is the origin, right, then M1 is where? X1 is L1 sine theta 1, right? And Y1 is what? Minus L1 cosine theta 1, right? And this one, we've got X2 is X1 minus apparently, well, I guess if we just think about the picture of them being the same, I'll write a plus here. My picture is just for negative theta 2. So a plus L2 cos theta 2, excuse me, sine theta 2, if I could do math, the same reason as the other one, trigonometry, and Y2 would be Y1 minus L2 cos theta 2, right? Which, of course, we could write that out. That's L1 sine theta 1 plus L2 sine theta 2 and L1 minus L1 cos theta 1 minus L2 cos theta 2. And you tell me what happens when I look at x1, you know, x1 dot squared plus y1 dot squared. What's that going to work out to? And likewise for x2. Because that will give me the speed for each in terms of the variables involved here. So like x1 dot is L1 cos theta 1 dot. And y1 dot is minus, well, plus L1 sine theta 1 dot. So when this is just going to be L1 squared theta 1 dot squared, right? But this one, when I square these out, I get, when I differentiate it, I get the cross term in the middle, I think, canceling. Let me think about it. I'm going to have an L1 squared theta 1 dot squared, right? From these two. But I get also plus an L2 squared theta 2 dot squared. And my question is there a middle term? You know? Because I'd have I was trying not to write all this out. L1 cosine theta 1 dot plus L2 cosine theta 2 dot. That's my x2 dot. I square that thing and I add it to y2 dot squared, which would be L1 sine theta 1 dot plus L2 sine theta 2 dot. Square these. This is x2 dot squared plus y2 dot squared. As I pointed out, it already gives us this term and that term. The cross terms, I get a theta 1, theta 2, I get cos theta. Oh, I do think I get something, don't I?
Yes.
I get L1, L2, cos theta 1, cos theta 2, plus sine theta 1, sine theta 2, right? Theta 1 dot theta 2 dot squared? Maybe not squared, just when I square it I get no, just that, right? But of course this is what? This is cosine of theta 1 minus theta 2, or vice versa, whatever you like. right? All right, so the Lagrangian for this then is what? M over 2, well, M1 over 2, L1 squared, theta 1 dot squared, plus M2 over 2 times L1 squared theta 1 dot squared, plus L2 squared theta 2 dot squared, plus L1 L2 cosine of theta 1 minus theta 2, theta 1 dot, theta 2 dot. That is just my kinetic energy so far. And then the potential energy here is easy. We just do potential energy is simple enough. Potential energy is like M1G Y1 plus M2G Y2. That's all it is, because we put potential energy to be 0 at the pivot point just for our convenience. We can make it 0 wherever we want as it happens. That's a gauge freedom. So we got my plus, because of the, again, we do subtract the potential energy, so we do minus a minus is a plus. M1 L1 cosine theta 1, and then my Y2, this bad boy down here, plus M2 L1 cos theta 1 plus L2 cos theta 2, if I haven't made a mistake. Maybe I haven't made a mistake. It's possible. Stranger things have happened. There is the Lagrangian for the double pendulum. And then, yeah. And then, of course, you can calculate the Euler-Lagrange equation and find out how the one angle varying makes the other angle vary, and this gives you the motion of a double pendulum. And of course, the motion's coupled, and it's pretty wacky if you actually watch it, right? But if you can do this, you can just as well do a double, like a triple pendulum. It's just it's a simple matter of just writing down coordinate formulas, differentiating them, learning how the rate of change of one is related to the other, so that you can meaningfully write down the speed for the system. And then potential energy due to gravity is relatively simple to write down. And then you can add in other fun stuff like springs and things. But so that's Lagrange. Now another example. Suppose you had a ball that is just rolling, on this ball of radius m that's rolling without friction. So it's just gliding along the surface of a bowl of radius r. So we can say that that's x squared plus y squared plus z squared equals to r squared, okay? I'll put the origin down here. Then you can ask, well, what's the equations of motion for such a thing? All right, so in other words, this translates into just r equals to r, which means that, of course, r dot is equal to 0 here. So my Lagrangian, m over 2, I just go back to my spherical one that we worked out earlier. R dot in this case is 0. So I've got r squared theta dot squared, right? Plus r squared sine squared theta, phi dot squared.
So not moving down because of gravity either.
This is the kinetic energy. It's moving. I'm saying it's moving. It's going around the bowl, all different which ways. So then I just do minus mgz, right? Mg, but what's my z? Well, my z, spherical coordinates, right, is r cosine theta here, minus mg r cosine theta. That's the Lagrangian in this situation. And so, for example, like the partial L partial theta, well, let's do partial L partial phi. It's kind of more interesting in some sense. ddt of partial L partial phi dot. What's that give me? There is no phi dependence, so that's 0. And on the other hand, we have ddt of partial L partial phi dot, which is m r squared sine squared theta phi dot. So again, this is a conserved quantity of the motion, which essentially corresponds to the radial angular velocity. R sine theta is the radius from the from the center axis here. All right, so like whatever kind of if it's I don't know exactly the motion, but just suppose it's like something like that. Like whatever it's got angular momentum around the z-axis like that, it stays what it had to start with in that sense. But of course, the angular momentum that corresponds to like this kind of motion, the sweeping of the other angle, the theta angle for physics, the one that's off the z-axis, well, that couples into gravity. So it's not conserved, it's more complicated. And the equation of motion for the theta coordinate is this. So partial L partial theta is, m r squared sine theta cosine theta, yeah? Differentiating this, phi dot squared. And then I've got that's my part, my bad, plus mg r sine theta, right? This is all my partial L partial theta, right? And that's equal to what? It's equal to the time derivative of partial L partial theta dot. Well, what is partial L partial theta dot here? The theta dot is just here. So that gives me an m r squared theta dot. So what is this? Well, this is like angular momentum with respect to the theta variable. It's the one that's sweeping like up and down. If my picture again. So this is theta. So it's like this kind of sweeping, which has to do with the z, which is why it's not conserved, because there's a torque on it. The torque is from gravity, right? That's this term right here. That's the torque from gravity. And this over here is something else. What is that? What do you think that is? So if this is apparently from gravity, what's this? Let's remember the whole problem. We're talking about a bead that's sliding freely on a bowl of radius r, right? So that has to figure into the story, right? And so what that term there is, I believe this piece right here is coming from the fact that it's on the bowl. The shape of the bowl. This is from the normal force of the bowl on the ball. Now, so the way I just did it is one way you can solve problems, but there's a beautiful and more elegant way to solve these kinds of problems using the method of Lagrange multipliers for Lagrangian mechanics. Let me show you how this looks in that approach. You'll notice I am having the good sense to not try to solve any of the differential equations that we're coming to today, because that's really another course altogether. My mistake last class was actually getting into the weeds and trying to solve the Brookstra problem. This is just stupid. So look, so it's very simple. You do this. L equals to m over 2. Check this out. R dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. That's my kinetic energy in spherical coordinates. And then I've got my mgr cosine theta. There's my potential energy. So you're like, well, but wait a minute, don't you know r equals r? So this is the difference. We do not impose the condition. We do not impose the condition r equals r in the Lagrange multiplier approach. In the Lagrange multiplier approach, we level up a dimension and solve the problem with more variables free. So essentially, instead of imposing the condition that little r equal to big R, which is to say that you're on the surface of the bowl, you say, no, I'm just going to let little r be free. I'm not going to say little r is equal to big R at the start. But what I'm going to do is I'm going to add an algebraic variable, a Lagrange multiplier, like here. And I forget if it's supposed to be plus or minus. I think it's plus lambda. And then you just put the defining equation. And the thing is, this works. Yeah, it works for the equation for the bowl, which is r equals to r. So you just do like r minus r. Because that's 0, right? So you're just adding 0 to the Lagrangian. But we're also now, like, L is function of r theta phi in lambda, as well as their derivatives in principle. Now, for the Lagrange multiplier, that is not interesting. I mean, the equations of motion for the Lagrange multiplier are always algebraic. So like, when you do the Lagrange equations for the, like, check this out. So like, partial L partial lambda equals to d dt of partial L partial lambda dot. Well, what happens there? Partial L partial lambda is r minus r, right? There's no lambda anyway. And that is 0. So one of your Euler-Lagrange equations is the constraint equation. Like, this builds in the constraint equation as a Lagrange equation, but it does more than that. It does more than that. Check out what it does for this partial L partial r d dt of partial L partial r dot. What happens there? Well, partial L partial r is giving me that one. So you've got your m r theta dot, right? m r theta dot plus m r sine squared theta. Oh, and that was supposed to be theta dot squared, right? Theta phi dot squared. Okay. And then what else? Oh, this one, right? So minus mg cosine theta. All right. What else? Oh, plus lambda, right? And that's equal to what? Partial L partial r dot, which is what? Well, that's just mr dot. So this is literally mr double dot. Trying to think if I can explain. I mean, obviously, so this is the radial acceleration has different pieces, right? It has the piece which is due to the force of gravity. And then, of course, it has this thing right here. So, like, the meaning of the Lagrange multiplier ends up being like the contact force. In this sense, I think. So like you can interpret the Lagrange multipliers as contact forces themselves. If I solve that for lambda, it gives me a formula for the contact force as a function of these things. Of course, this ends up being 0 when we plug in the constraint, right? So we can solve this for lambda, and it literally gives us a formula for the normal force on the ball to keep it on the sphere. And we can go on like this, but anyway. This is a very powerful technique. If you have a problem that's governed by constraints, if you use the method of Lagrange multipliers, you can gain a lot of insight into the constraints. This story continues for theoretical physics. Like theoretical physics is full of this kind of trickery where they introduce new variables which are sometimes thought to be unphysical because the equations of motion for the new variables are just, well, algebraic. They don't have any quote-unquote dynamics. There's no time dependence to their equations of motion. And yet, sometimes these kind of introductions of new variables are very, they give really deep insights into things. That's very roughly the idea behind things like, well, they introduce things called they introduce these things called ghosts and other things in the classical field formalism. Oh, okay. So one other thing I should talk about is there's also a method. The other thing in classical mechanics you might think about is so-called Hamiltonian mechanics. So the Lagrangian mechanics writes the Lagrangian as a function of the coordinates and their velocities. The Hamiltonian mechanics, on the other hand, it replaces the Lagrangian with the Hamiltonian, which in the simplest case, Hamiltonian is just equal to T plus U. So it's literally the total energy. But the thing is, so like here for one-dimensional, well, for two-dimensional motion it looks like this. Something like px squared over 2m plus py squared over 2m, plus your potential energy as a function of x and y. So h is a function of momentum, or momenta. All right. So you have to convert kinetic energy from being in terms of speed to being in terms of momentum. And you might well be like, well, okay, maybe I know how to do that for x and y velocity, right? I mean, that's easy enough, right? Px is what? It's, mx dot, right? And what's the y momentum? Well, it's my dot, right? But what's the theta momentum? What's the momentum with respect to theta? See, that's a more difficult question, but the answer is actually already given to us in the Lagrangian formalism, because if you look at this is exactly what you'd like to be the momentum in the phi direction. And like this over here is exactly what you'd like to mean by momentum in the theta direction. So basically we just say the momentum is like partial L, partial Qi dot. So if you have a Lagrangian written in terms of, coordinates, generalized coordinates Q, Qi, Q1, Q2, Q blah, blah. Well, the generalized momentum, you simply look at the partial derivative of the Lagrangian with respect to the velocity for that generalized coordinate that defines the generalized momentum. So there's a straightforward procedure from converting from the Lagrangian formalism to the Hamiltonian formalism, and vice versa. This actually brings us into something called the Legendre transformation. There's much more to say here. Like in the Lagrangian, in some sense, you're like looking at trading integrals over momentum for integrals over coordinates. If you take a broader view of this, there's more to say here. But anyway, so But that's pretty much it. And then, well, not it entirely. The Hamilton's equations, goodness gracious, I forget right offhand, sadly. But there's like two Hamilton's equations which basically correspond to like conservation of energy, and they're first order differential equations, if I remember right. But the Hamilton formalism more naturally generalizes to like quantum mechanics. So like in quantum mechanics, we look at the Hamiltonian, which is like the quantum version of this, and its states are energy eigenstates and so forth. And so like the people who wrote down quantum mechanics deeply understood both Lagrangian and Hamiltonian mechanics. And so when they wrote down quantum mechanics, it was like a natural extension of this. So if you really want to understand quantum mechanics very, very deeply, you really need to invest like a solid year in classical mechanics at least. More than I have. You need to understand wave mechanics deeply, as they did when they wrote down the theories of quantum mechanics. And I think that knowledge is largely lost in the physics community. We just accept quantum mechanics as if it's something that is impossible to understand. And then when we're near retirement, we try to find a meaning. At least that's what I see happening. Because
Is that related to the group,
the Hamiltonian,
yeah.
the group of the Hamiltonian?
Algebra.
Oh, like the Hamiltonian algebra? Oof, I don't know. There's the Heisenberg algebra. But anyway, the Hamiltonian viewpoint seems to be more, well, I don't know. You can find papers going both ways. Like the Hamiltonian viewpoint's fundamental, and people are like, no, the Lagrangian viewpoint's fundamental. People can argue all day long about this, about which one's easier to think about quantizing and turning into quantum mechanical systems. Like, I don't know. I think there's room for argument there. I haven't taught physics at this level long enough to have a properly dogmatic opinion on the matter. So, but anyway, now you have seen a little slice of what it's like to be a junior in physics, right? This is the junior level physics is what you're looking at. This and homeworks like it, solving these things, all in vector formalism, is what makes junior level physics at least 10 times harder. At least 10 times harder than the physics course that the general engineers complain about, the 231, 232 course. When I was in physics and we took these courses, we were all like flabbergasted. We were like, how is this so hard? But the thing is, once you do a year of this, it unlocks things in your mind that were previously locked, and like it opens up a new way of seeing through math. It's unfortunate. Like if I had my druthers, I would make all math majors take a year of junior level physics just to really come to terms with how to solve equations, because by and large, yeah, we have hard proofs and things and existence, this and that, but do we really solve really, really hard equations? Not too much. In these things, you will find hard equations which seem insurmountable, and yet there's an answer in the back of the book which you can't get to. And it can be got there, but it is so much algebra, so much algebra. But anyway, and then physicists react two different ways. The one way physicists react is like, oh, this is beautiful, I should accept my fate and like learn to get good at math. The other way is some people are like, well, real world problems aren't pretty like this, so we should just numerically approximate everything. So you'll find a certain camp of like people who teach classical mechanics who bring spreadsheets into it so they can numerically approximate everything. And then there's other people who are like more like, well, no, I mean, if you want to solve that on a computer, go for it, but the class is going to focus on the beautiful stuff. And I don't know, there's, opinions vary, but anyway, that's it for this part of the course. I'm going to move on to let me get back to the math. I guess this was math though, right? I don't know.